Buddy, this video is going to cover exponential growth and decay, and our last video was all about graphing exponential functions, and we saw exponential functions that were like this, that increased over time, some that decreased over time, and stuff like that. What's really important about exponential functions is that they are not lines, so there should be some type of curve in them. This video is going to cover the growth and decay part of a function. So growth would be something that gets larger over time. This would be an exponential growth function. This would also be an exponential growth function. The difference here is there's always a floor or a cap for these functions. That cap can be the very lowest level, or it can be the highest level. It still is exponential growth. And then an exponential decay would be something that gets smaller over time. What I like about exponential growth and decay is it allows us to do many real-world problems pretty easily. So let's get started. The growth and decay formula is always written as y equals p times r to the t power. A lot of times you'll see it written as I equals PRT, and you'll hear me say the PRT function a lot. But what does the P, the R, and the T mean? Well, the P stands for principal, and principal is a banking term mostly that means your starting value. So for example, if I have a bank account, my principal would be how much money I put in the bank account. R then stands for the rate of whatever that exponential growth or decay is, and we think of rate as a percentage, and you always want to think of it as a percentage that is rated over 100%, either up or down. So you always want to root it back to 100% increase or decrease from there. And then finally the T, probably the one that you could have guessed on your own, stands for time. But it's very important to know if we're looking at years, months, weeks, that type of thing. It's very easy to mix those up. So to use the PRT function correctly, let's do a couple small examples to build a function. So we want obviously to have y equals p times r raised to the t. $1,000 is what we start with, so that would be our principal. That would stand in for our P. So I would go 1,000 times something. Now our 8% annual interest, annual means per year, that would be our interest rate. And now it might be tempting to put a 8% in here. But you always want to think about if 100% is your total, what is 100% plus our 8% increase? Well, that would be a total of 108%. But you wouldn't write a percentage in an equation. You would write the decimal 1.08, which stands for an 8% increase over 100%. And then finally, it asks over 5 years. And since our interest rate is annual, that means this interest ticks 5 times. So we have made the equation 1,000 times 1.08 raised to the 5th power. What's very important is that it's this raised to the 5th power, not 1,000 raised to the 5th power. Here we have a $1,500 with a decrease of 5% every year. Same idea as before. We obviously want to do the P times r raised to the t function, or the PRT function. Our P in this example would be $1,500, which is our starting value. Now this time we want a decrease of 5% every year. So if we start with 100% and then we want to decrease 5%, that means we are left with 95% every year. 95% written as a decimal would be like this. And then it does not tell us t. So we are actually going to leave this as a t. And now if we're ever graphing on Desmos, the t is going to be left alone or written as an x, because we want to make an equation and you need a second variable to make a graph. If you show me this slide written out, you get 5 SPs. So let's get into a real world situation. Sam opens up a bank account that starts with $500 to save up for college. So I see starts with $500. That jumps out at me as probably really important. Each year, she gains 5% interest. So that's probably our rate over time. And the question asks, how many years will it take to have $1,000 saved up? So we're trying to get to $1,000. And we've been doing a lot of graphing recently that will look like graphs like this. But these numbers are way too small for the graphs that we're working with. And we're only going to care about positive numbers. So we are not doing graphs like that anymore. We want to be only looking at positive graphs. And we want to be thinking about, with our x and our y coordinate, what will go where. So in order to make our equation, we once again want to do the y equals p r t function. Well, this certainly looks like our principal, or our 500. So it's y equals 500 times, and this year she gains 5% interest. So if we start at 100% and we want to increase by 5%, whoops, we probably not write it like that yet, by 5%, that means we will have 105% each year. Okay? So that will be, as a decimal, 1.05, and then raised to the t. And we want to know how many years up here in t will give us an answer of 1,000. So what we would do here is we would make ourselves a table. And for year 1, we would do 500 times 1.05 raised to, the 1 for the year. And we'd get out our calculator and we'd do 500 times 1.05 raised to the first power, which would be $525 that Sam would have after the first year. Here for year 2, we would do 500 times 1.05 raised to the second, or we could just do this number times 1.05. And so we would do that again. And we would get $551.25. And we could go over here and we could make ourselves a graph. But I will tell you, the best thing to do in this situation is to use the program that we've been working with all year, which is Desmos. And here I graphed our equation. The problem is I don't see anything on Desmos. And well, that's because our starting number is 500. So we need to zoom way out, and there it is. So I see my 500 right here, and the question wants to know, where do we get 1,000? So I go up here, and I get as close to 1,000 as I can, which is really close to right about there. And so I would say it is really close to 14 2/10 months. So I would get rid of my table here, because we're not actually going to end up doing the table for this problem because we use Desmos. And you would say, it will take Sam really close. Whoops, there we go. To 14 2/10. I said months earlier, I mean years. To raise $1,000. Now, the other thing that's really nice about Desmos here is if you see this button right up here in the top where it says Edit List, if I click that and I click this button right here, it will actually convert the data to a table for me. So I actually don't necessarily need the graph here on the side, because what I can do is I can type in a number and it will plug it into the equation automatically. And so, you know, if I go 13, 14, 15 is too big, and I can kind of use that to help me narrow down the number that I think is closest to the exact number that I want in the situation. But that was a really quick run through for exponential functions. What in the retake video, I'm going to cover a few more examples, give you a few more realistic real world problems. But for now, if you have any questions, please let me know.